Today we will be taking notes on 11.2, Power Generation and Transmission. We will be discussing the following topics: AC generators, average power and root mean square values of current and voltage, transformers, half-wave and full-wave rectification, diodes, and capacitors. Let's begin. There are two kinds of current. We have focused mainly on direct current, which is where the electric charge flows in only one direction. In the animation, you can see the current flowing consistently in one direction. There is another form of current called alternating current, or AC. As its name implies, the current alternates, or changes between directions periodically. Notice we have a new symbol used to represent a power source that allows current to flow in alternating directions. We were introduced to alternating currents when we talked about the motor effect, when a loop of wire conducting current was placed within a magnetic field, which resulted in opposing forces on either side of the loop that caused the coil to rotate. Direct current was made famous by Thomas Edison, who advocated for this form of energy to power homes, and he was pushing for the powering of towns in the 1880s. One problem with DC is that it is not easily converted to high voltages, which meant there would need to be multiple power plants located near each neighborhood so that people could get power. When people connected to the power, the voltage dropped a little. This small drop meant that the power plants would have to be located within a mile of the place where the power was being used. This made it extremely difficult to supply power to people that lived further out of the city. Nikola Tesla, however, is credited for producing alternating current, or AC. Transformers made it possible to create a range of voltage, from thousands of volts to the normal 110 volts or 220 volts that normal households use today. Through higher voltages, the same power could be transmitted at a lower current, which meant less power lost due to the resistance in the wires. As a result, large power plants could be located many miles away and more people could receive power. The battle between these two greats was so long and intense. However, Tesla's alternating current won out for supplying power to the masses. Most homes are built for AC. We commonly use an alternating current of 60 Hertz, or the current that alternates 60 times every second. DC has its uses. DC is used in almost all electronics, such as cell phones, flat-screen TVs, flashlights, and some hybrid electric vehicles. That being said, realize that we get the power to our homes and buildings as AC. But then we have to convert that AC into DC, because that is what our devices and appliances use. This means that some of the energy is lost in this conversion. But enough about that. Let's get on with the notes. We discussed how alternating current, or AC, is when current switches between two directions consistently. It uses generators to produce energy, which converts mechanical energy to electrical energy. This is the most common way that we generate energy, and this is the way we receive power to our homes and buildings today. The following must be present for an alternating current to be achieved. There must be a coil, a magnetic field, a connection to an external circuit, and some relative movement between the coil and the field. This means that either the coil is rotating around a fixed magnet or the magnet rotates around a fixed coil. On the left, we see a familiar diagram of the bicycle dynamo. The wheel of the bike turns a magnet inside a coil, which then induces electricity to run the bicycle's lights. On the right is the other example we have touched on in a past video, and it is an AC generator that has fixed magnets and the coil rotates. Let's discuss what's happening in more detail. Here we see two poles of magnets, a north and a south, surrounding a rotating coil. A galvanometer is connected here. As the coil rotates perpendicular to the magnetic field, the wire loop cuts the lines of the magnetic force at different angles. Because the coil's orientation is changing in relation to the magnetic field, the magnetic flux is constantly changing. This change in the magnetic flux induces an EMF. If the rotating coil is connected to an external circuit, an electric current flows. The amount of induced EMF in the loop at any instant of time is proportional to the angle of rotation of the wire loop. So here we have the coil, and we have the coil that is in between two magnets, and we see that this angle consistently changes. As this coil is rotating in a complete cycle, we create one full sine wave. Let's explore this in more detail. Look at the picture below to the left. When the coil lies parallel to the magnetic field, then the magnetic flux linkage is maximum. The coil cuts through the magnetic field lines and moves at a maximum current. So here we have the EMF being at its maximum. When the coil is upright, as seen in the bottom right diagram, the field lines lie in the plane of the coil. There is no change in the magnetic flux, and the EMF is zero, as you can see on the graph at these 2 points. And this is because the coil is not cutting across the field lines. So we can achieve an induced EMF of 0 when the coils are perpendicular to the field lines, and maximum when the coils are parallel. When the wire is rotated past the 180-degree point and moves across the magnetic lines of force in the opposite direction, the electrons in the wire loop change and flow in the opposite direction. Then the direction of the electron movement determines the induced voltage. So we can see that when the loop or coil physically rotates one complete revolution, or 360 degrees, one full sinusoidal wave is produced. Here is an example for you to try. A coil rotates at a constant rate in a uniform magnetic field. The variation of the EMF with angle theta between the coil and the field direction is shown. Copy the graph below, and on the same axes, add the EMF that will be produced when the rate of the rotating coil is doubled. Explain your answer. Go ahead and pause the video and do this in your notebook, and then start it back up when you're ready to check your answer. The answer is that the rate of change of the flux linkage would double. The magnitude of the peak EMF will also double due to Faraday's law, which states that the induced EMF is proportional to the rate of change of flux linkage. Because the coil is now rotating in half the time for one cycle is then halved. So here we see we have twice as many wavelengths in the same amount of space. There are things that we can do to increase the EMF. We could increase the number of times the coil is rotating in a given amount of time. The magnetic field strength can be increased. We can increase the number of turns on the coil, or we can also increase the area of the coil. For example, if you were to double the rotational speed, you can see that the EMF would also double. When measuring alternating currents and voltages, it is useful to define an average current and voltage. Unfortunately, the average values for voltage and current over one cycle is 0. If you look below at this graph, for one cycle, there are positive half cycles and there are negative half cycles. If we were to take an average of this, the average value would then be 0. To help us get around this, we use the idea of something called the root mean square of the voltage and current. The root mean square of voltage and current is an easy way to define voltage or current of AC waves in terms of average power. The first step is to square the voltage to get a quantity that is positive during the whole cycle. This gives us the max power, and that is P sub max equaling I naught V naught. Notice that the data points are all in the first quadrant, as is seen in the red solid lines. Step 2 is to find the average of this positive quantity. When you're finding the average, we get the equation of P equals 1/2 I naught V naught. The red solid line shows this average. Step 3 is to find the square root of this quantity to show the RMS of the voltage. This is also the direct current equivalent. We get V sub RMS equaling V naught divided by the square root of 2. And we can see that now this value right here, which is in the solid blue, is called the root mean square, and it is the direct current equivalent. We know the instantaneous power dissipated in the component is P equals I squared R. Here we have a graph that plots the current versus time of an AC generator. If we were to square the current, we would get I squared. And the pattern is shown in brown, and it is in the first quadrant. The mean value of I squared is equal to I squared divided by 2. And this is our root mean square of the current. This is the maximum or peak value of I, and that is shown by the dotted brown line. The root mean square value of the current is therefore I equaling I naught divided by square root of 2. Because the resistance is the same in both of these cases, we can say that R equals V naught divided by I naught, which is equal to V sub RMS divided by I RMS. A transformer is an electrical device which either increases or decreases the magnitude of an alternating voltage by utilizing the phenomenon of electromagnetic induction. There are 3 parts that make up a transformer. The first part is the input or primary coil. The second part is the secondary coil, also known as the output coil. And then there is the iron core with which both coils are wound. So how does a transformer work? Well, we know that when a current is flowing in a solenoid, there is a magnetic field that is produced. When there is an alternating current in the primary coil, this produces a changing magnetic field in the iron core. This magnetic field is linked to the secondary coil with the iron core. The fluctuating magnetic field from the iron core induces a current in the secondary coil due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across this secondary coil will be the sum of the individual EMFs induced in each turn. So here we have epsilon sub S for secondary equals the EMF times the number of turns. Likewise, the sum of the primary coil's EMF is also the same, which is determined by the EMF per turn, which would then give us epsilon sub P, P for primary, equaling the EMF times the number of turns. If we rearrange these 2 equations to solve for the EMF per turn, which is V, we would get the total EMF divided by the number of turns. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for the primary and secondary coils will be the same. We represent this as Vp equals Vs. Because the secondary coil's EMF is equal to that of the primary coil, we can set these equal to each other, and it can be expressed as seen in this equation here. Keeping the law of conservation of energy in mind and assuming that there is no loss of energy in the transformer due to resistance, meaning that the resistance is negligible, the energy that enters the primary coil is equal to the energy leaving the secondary coil. So we can say the following, that the total EMF of the secondary coil times the current of the secondary coil equals the total EMF of the primary coil times that of the primary current. This can also be represented as E sub P divided by E sub S equals I sub S divided by IP. So here are some equations that are represented in your data booklet. If we were to take the first part and solve for the sum EMF of the secondary coil, we would get epsilon sub S equals epsilon sub P divided by the number of turns for the primary coil times that of the number of turns for the secondary coil. This simply means that if you have fewer turns in the secondary coil than that of the primary coil, you could actually lower the voltage. This is called a step-down transformer. If there are more turns in the secondary coil than that of the primary coil, we can actually increase the voltage, which is known as a step-up transformer. To find the efficiency of a transformer, you need to take the energy that is supplied by the secondary coil, divide it by the energy supplied to the primary coil, and multiply it by 100%. The efficiency of a transformer can be improved if the core is laminated so as to increase the electrical resistance and reduce the current. Choosing a soft magnetic material for the core and low resistance material for the wires can also improve efficiency. The design of the transformer itself can alter the efficiency by creating the maximum rate of change of flux linkage. When current passes through a wire, the power dissipated, or losses heat, is equal to P equals VI across the wire. Since V equals IR, we can state that power dissipated is I squared times R. Since the loss of power depends on the square of the current, when transmitting energy over large distances, it is important to keep the current as low as possible. However, to transmit large quantities of energy, we therefore must have a high voltage. Through the use of AC generators, we are able to transmit electricity at high voltages and low currents over long distances. This is achieved by using step-up transformers and then step-down transformers. This allows the normal household to take advantage of the electricity without having to be close to the power source. All electric devices require constant power. This is problematic if our power comes in the form of alternating current. Because the alternating current switches polarity from positive to negative to positive to negative, there are periods of time when there is no output of energy at all. As you can see here, we have all positive or all negative. Direct current has the current and voltage as either all positive or all negative. We need to have a way to change alternating current into direct current. We call the process of converting AC into DC rectification, and the device that converts AC to DC is called a rectifier. A rectifier allows portions of positive or negative signals to pass to the device. To do this, rectifiers use something called diodes. A diode is a device that allows conventional current to flow in one direction from positive to negative in the direction of the arrow. A diode is called forward biased when the current passes through positive to negative, and it is called reverse bias when the current blocks negative to positive current. There are two kinds of rectifiers you will be expected to understand, and they are classified according to the period of conduction. The first is called a half-wave rectification. A half-wave rectifier rectifies only one half of the cycle of the waveform. It consists of a simple circuit. A single diode is connected in series with the secondary terminals of a transformer and the load resistor. Notice how the load resistor is located after the diode and receives the rectified current. The resistor represents the device we want to power and is sometimes also referred to as the load resistor. During each positive half cycle of the AC sine wave, the diode is forward biased, resulting in current flowing through the diode. During each negative half cycle of the AC sinusoidal input waveform, the diode is reverse biased, and therefore no current flows through the diode or the circuit. So, although we have managed to make the current going to the device flow in only one direction, the current is not constant. We see that there is some time between when there is no power that is released. We need to fill in these gaps of no current so that we have a consistent supply of power. We can achieve this by creating a parallel circuit that incorporates a diode, a resistor, and a capacitor. A capacitor is a device that temporarily stores electric charge. Note how the resistor and capacitor are located between the diode and the load. During the first half cycle, the capacitor charges up, and its PD increases to the PD of the transformer. In the second half cycle, the current drops to zero, and the capacitor discharges its electrical stores. The cycle of capacitor charging and discharging causes a small variation in the output potential difference, and you can see this here. So this is where the capacitor discharges, and this is during the spot when there is no current. So what this creates is something known as the ripple voltage. Half-wave rectification is suitable for some low-powered applications. However, in many cases, an even smoother and consistent DC supply of voltage is required. Using every half cycle of the input voltage instead of every other half cycle helps produce a smoother, more constant DC supply. This is called a full-wave rectifier. A full-wave rectifier is pretty much just a parallel circuit with a resistor and two diodes. The diodes are connected to the transformer's secondary coil, and it is usually in the center of the secondary coil. And this helps to further smooth the rectified DC. Each diode takes turn to supply current to the load. When point A of the transformer is positive with respect to point C, diode D1 conducts in the forward direction as indicated by the arrows. When point B is positive in the negative half of the cycle with respect to C, diode D2 conducts in the forward direction, and the current flowing through resistor R is in the same direction for both half cycles. Looking at the resultant output, you can see a full wave rectifier creates twice as much voltage output than a half wave rectifier. If you added a capacitor to the full wave rectifier, you get an even smoother resultant output of voltage. So here we have the ripple voltage that is closing off a little bit of this empty space so that we get more voltage and it creates a smoother output. A diode bridge is 4 or more diodes in a circuit configuration that provides the same polarity of input. Here we see 4 diodes, diode 1, 2, 3, and 4. They are arranged in series. How this works is that only 2 diodes conduct current each half cycle. So here we have the 4 diodes. During the positive half cycle of the supply, diodes 1 and 2 conduct in series while diodes 3 and 4 are reverse bias and the current flows through the load as shown below. During the negative half cycle, diodes 3 and 4 conduct in series, but diodes 1 and 2 switch off as they are now reverse biased. The current flowing through the load is the same direction as before. Now, if we have a smoothing capacitor added into a circuit with a diode bridge, we would be able to convert the full wave ripple output of the rectifier into a smooth DC output voltage. So here we have a capacitor put into this circuit, which would then create a smoother output for the voltage. Here are a few practice problems for you to try. There are 3 parts of this one problem, and we have reached the end of our video. Be ready to use this information in class, and thanks for watching.